Hello, welcome back to the channel. In this video, I am going to discuss Cambridge IGCSE Physics Paper 6 Alternative to Practical, October-November 2023, Paper 62. Let us get started. Now, let us look at the first question. A student investigates the period of a pendulum. Fig 1.1 shows the setup. A, the distance D is measured from the bottom of the clamp all the way to the center of the bulb. I have to highlight this because this is very, very important. The student adjusts the length of the pendulum until D is equal to 50 cm. He displaces the bulb slightly and releases it so that it swings, something like this. Okay, you just imagine that I don't have the pendulum bulb. That is why I need to use a model in clay, right? I tried my best to make it looks like a bulb, right? So you just imagine this is a bulb. You just displace it a little bit. You let it go. Let it swing. And after 2 or 3 complete swings, he pressed his stopwatch to measure the time taken for 10 complete oscillations. Now the time is shown here, and this is digital stopwatch. First part, Fig 1.2 shows the reading on the stopwatch. Record in table 1.1 the time T for 10 complete oscillation. That's the reading over there. So you just read off 14.21 and then you just fill in the blank here, 14.21. Now, the second part, calculate and record in table 1.1 the period T of the pendulum. The period is the same, is the time for one complete oscillation, right? So the student completed 10 complete oscillations. That's the time. 14.21 is the time taken for 10 complete oscillation, right? So if you want to find the period, because it is time for one complete oscillation, you just say T divided by 10. So I have 14.21 divided by 10, right? That is 1.421 second. Right, but before I write down my answer, I look at the T, the period, when D is equal to 100 cm. Look at the significant figures of the period here. It is 3 significant figures. So you need to bear in mind that the period can only be recorded in 3 significant figures. So you have to round it off to 3 significant figures. I round it off to 1.42. 3 significant figures. Remember that. Now, third part, calculate t squared and record your value in table 1.1. So t squared, you just take the period 1.42, you just square it and make sure that you put it in terms of 3 significant figures as well. 2.02 is my answer. Right, because period square depends on the significant figures of period. Period takes 3 significant figures. That is why period square would take 3 significant figures as well. Now, the last part, write the units in the column headings. The unit in the column headings. Column headings means the title of your table. Table comes with the physical symbol, right? And together with their appropriate units. So the units of D is cm. You might want to ask, how do I know? Okay, let us scroll out a little bit. Could you see here? D is equal to 50 cm. That is how I know. And T is the time measured in second. Period is also time measured in second. T square, this is period square. You have to take the second, you square it. So it is second square. Now B, the student repeats the procedure in A using D is equal to 100 cm. The readings and results are shown in table 1.1. Another student suggests that, T square is directly proportional to D. Wow, that student must be very, very confident. Explain briefly how to test a suggestion using the results in table 1.1. I only have 2 results. When you have lack of the result, right? Only 2 results. How do I plot the graph? I cannot plot the graph, right? The best way, to see whether this relationship is valid. How do we do? Right now, whatever the students suggested, students say that, this is t squared, directly proportional to d. And to get rid of this proportionality symbol, we put t squared is equal to constant times d. Since I have 2 readings here, I can compare my value of k. K is a constant, right? So if I get the constants values, right, or only slight difference, small difference between the K values, then I would say that, okay, agree with this suggestion that T square is directly proportional to D. That is why I find K1 is equal to T1 square over D1. K1 refers to 50 cm. The first K value. So I'm going to write it here. K1 is equal to T1 square, period 1 square over D1. Period 1 square is 2.02 second square divided by 50 cm. And here I got 0.0404 second square per cm. K2, I use period 2 square divided by D2 value. That is 4.08 second square divided by 100 cm. Here I got 0.0408 second square per cm. Now I find the difference between the K value. So difference between the K value is equal to K2 minus K1, which is equal to 0.0408 second square per cm minus 0.0404 second square per cm. And I got 0.0004 second square per cm. This is such a small difference, right? I would say that since the difference, yeah, between the K values is very small, I will have to agree with this suggestion, right? Since difference in K values is very small, T square is directly proportional to D. That's it. Now C, the procedure can be repeated to plot a graph. Yes, that is true. Suggest additional values of D that are suitable for the experiment. Okay, I want you to bear in mind, if you want to plot a straight line graph, right? If you confirm that this is a straight line graph, yes, it is confirmed, it is straight line graph because the student suggested that T square is directly proportional to D, right? If it is a straight line graph, you need at least 5 readings. The best is 6 readings to plot a nice bad speed line or straight line graph. So I would suggest 6 values since the students has already done for 2 experiments, 2 values here. I would suggest 4 more values. And first of all, this is about D. Student is using meter rule to measure D because D is in cm, right? And you have to bear in mind the maximum length that can be measured by a meter rule is 100 cm, right? It cannot exceed 100 cm. Now, the values must be more lesser than 100 cm. So I would suggest maybe 20 cm, 40 cm, or you could suggest 30, 35, doesn't matter. And I would suggest maybe 70 cm as well. Sorry, 70 cm and 80 cm, or you can suggest 90 cm as long as it is lesser than 100 cm. Right. Now, D, explain how you will measure the distance D as accurately as possible. Draw a diagram to help your explanation. Right. This is a diagram that I drew. But the diagram that I drew here, I only explain how to measure here, this part. All the way from the bottom of the clamp, okay, to where the surface of the bob is. Right, because of the length of the string to be more accurate, right? And D must be measured from the center of the bob. You know pendulum bob, okay, is a sphere. Now, the center of the bob represents the radius of the bob. The problem with the radius is that the bob itself is very small. And too bad, right? In our laboratory, we don't really have apparatus to measure the radius of the pendulum bob. The one that we have, which is considered very accurate to us, is this one. This is called micrometer screw gauge. Micrometer screw gauge, even though it is very sensitive, but it can only be used to measure the diameter of the pendulum bob. Now, I will have to measure the diameter of the pendulum bob first, and then to find the radius of the bob, I just take diameter divided by 2. How about that? Okay, so I will say that, okay, here, maybe I add a little bit, measure diameter of bob by using micrometer screw gauge. Radius of bob, right, is equal to diameter divided by 2. Done. And then, okay, why do I use set square 1 and set square 2 is that? I will explain. Set square 1 is used as a guide to read from meter rule. Because when you hang the pendulum bob, right, there is a certain distance between the bob, the string, and the meter rule. So I need a guide here to make sure that the value of D is measured as accurately as possible, right? And then you have to put a mark on the center of the bob, remember? That is, and the set square 2, because, okay, this one, I will just put it mark on bob so that the measurement of D is more accurate. Set square 2 is used to make sure meter rule is vertical. Right, because all the readings depend on meter rule. If the meter rule itself is not vertical, so my distance D would not be accurate. Right, that's the answer. E, explain why timing 10 oscillations gives a more accurate result for the period T than timing 1 oscillation. Now, I want to use the logic to explain this part, right? Because I noticed that most of the students, when they are asked to measure the period of one complete oscillation, whether it is related to pendulum, it is related to pendulum bob, it is related to play, it is related to oscillation of a ball, right? I just want to let you know that if you displace, because you're the one that conduct the experiment, if you displace this pendulum bob to a small distance and you release it and you take the stopwatch and you press at the same time, right? I'm just going to tell you that it doesn't work for me because my brain, I only have one brain, one head. I cannot do two things at once. I get confused. So I might be pressing the stopwatch a little bit faster, and you might be pressing the stopwatch a little bit slower. So one press faster, one press slower, that will give rise to a very, very inaccurate measurement right here, right? So the correct way to measure the period is that you take 10 oscillation. It is like this. You displace the pendulum bob a small distance and then you release it. Let it swing first. You relax, really swing 2 or 3 complete oscillation, right? Before you start your stopwatch and start to count. 1, a 2, a 3 until 10 oscillation, right? So as long as you feel comfortable and then you get accurate result. Why not, right? Now, why timing 10 oscillation? Remember what I say? You press faster. I might be pressing the stopwatch a little bit slower. That is to reduce humans' reaction error. Or you could also say that we time 10 oscillation because we want to decrease the percentage uncertainty of time measurement. Percentage uncertainty of time measurements means the error that could be caused by the measurements of time. So that is called percentage uncertainty of time, right? Number 2, a student investigates the resistance of a wire. Fig 2.1 shows the circuit used. A, the student places a sliding contact S at a distance L equal to 40 cm from B. She measures the potential difference, PD, V, across the length L of the resistance wire. She measures the current I in the circuit. The meters are shown in Fig 2.2 and Fig 2.3. Write down the current I. If you want the current I, you have to refer to Fig 2.3 because capital A is the symbol of the unit of the current, which is called ampere. So this is 0.2, this is 0.3, 0.32, 0.34 is the value of my current. Ampere is the unit. And the second part, record the potential difference V, reading in the first row of table 2.1. Don't worry about that. I will take my V reading first. This is 1.1. This is 1.2. It is 1.2 volt. So I just put it here. 1.2 volt. I'm done with that. B, the student repeats the procedure in A using L equal to 50 cm, 60 cm, 70 cm, and 80 cm. Readings are shown in table 2.1. First part, calculate and record in table 2.1 the values of resistance R using the equation R is equal to V over I. Oh, they are so kind. They give us an equation to use. Now, I'm definitely going to use that equation. But before that, I have to write down the reading of I first, which is equal to 0.34 ampere. Right, I have to put that first because the I value is not changing. Now, okay, for the first R, I am going to calculate using V over I, 1.2 divided by 0.34, and I got 3.5. And I put R in terms of two significant figures. Why? Because the reading of I and V are both recorded in two significant figures. R is the calculated data, so R value must follow the significant figures of its raw data, which are the significant figures of V and significant figures of I. Now, the second R, I'm using 1.5 divided by 0.34, and I got 4.4, two significant figures as well. And the third R is 1.8 divided by 0.34, and I got 5.3, two significant figures as well. And the fourth R, I got 2.1 divided by 0.34, and it is 6.2, two significant figures. And the last R is 2.4 divided by 0.34. That gives you 7.1, two significant figures as well. Now, part C, plot a graph of R, y-axis against V, x-axis. Start both axes at the origin, 0, 0. Draw the best fit line. So I have already drew my best fit line here. You make sure that all the points are being plotted correctly. Oh yeah, but before that, how do I skip the second part? Complete the columns heading in table 2.1. So you have to give the unit of the physical quantities here. L is measured in cm, V is measured in volt, R is measured in ohm. How do I know ohm? Right? So I learned Ohm's law. Or if you don't want to put ohms, it doesn't matter, right? If you don't remember the unit of R, doesn't matter. Look at the equation that they give you. The unit of V is V. The unit of I is ampere. Can you see that? Volt per ampere. Yeah, you can denote the unit of R as volt per ampere. Not a problem. Now, this is the best fit line. But, okay, you see the front part of the graph is a bit wasted because we have to start from origin. No choice, right? I have already plotted my best fit line here. Now, D, determine the gradient G of the graph. Show clearly on the graph how you obtain the necessary information. Remember, when you are calculating your gradient is equal to y2 minus y1 divided by x2 minus x1. Remember that? So in math, you need to show you have two coordinates. And what does this question mean by how you obtain the necessary information? That means they want you to show which coordinates that you take to calculate your gradients, and you show on the graph. I have shown mine. This is 0, 0, right? One of the points, one of the coordinates that I use is 0, 0. The other coordinates that I use is 2.2, 6.6. Now, yeah, use a normal way to calculate my gradient, y2 minus y1 over x2 minus x1, and I got 3.0. And bear in mind, this is a range given in the mark scheme, 2.8 to 3.2. The value of the gradient must be spread between 2.8 to 3.2. Larger than 2.8, smaller than 3.2. Thank goodness mine is within the range, and I hope yours within the range as well. Now, question number 3. A student investigates the cooling of water under different conditions. Fig 3.1 shows the setup. A, the thermometer in Fig 3.2 shows the room temperature, theta R, at the beginning of the experiment. Record theta R. Now let us see. This is 20, 21, and this is 22 right here. So I put 22. Don't forget about the unit. It is degrees Celsius. The unit is there. B, the student pours 200 cm cube of hot water into the beaker. He places the thermometer in the water. He records the temperature theta of the hot water at time t equal to 0. He immediately starts a stopwatch. He records the temperature at 30-second intervals. Temperature readings are shown in table 3.1. First part, write the times in the first column of table 3.1. Remember, the question told you the temperature at 30-second interval. And the students start from 0 second. So 0, 30, 60, 90, 120, 150, and 180. So we are done. Second part, complete the column headings in table 3.1. So time is measured in second, theta is measured in degree Celsius. That's all. Now, C part 1, calculate the decrease in temperature delta theta 1 between time equal to 0 and time equal to 90 seconds. Time equal to 0 is 95 degrees Celsius and time equal to 90 seconds is 72 degrees Celsius. So delta theta 1 is equal to 95 degrees Celsius minus 72 degrees Celsius. So the answer is 23 degrees Celsius. So I'm going to write here 23 degrees Celsius is the answer. And the second part, calculate the difference in temperature delta theta S between the temperature at time t equal to 0 and room temperature theta R. Room temperature is 22 degrees Celsius. So from 0, 95 minus 22 degrees Celsius. Right, so delta, be careful with the value that you sub in. Theta S is equal to 95 degrees Celsius minus 22 degrees Celsius. So the answer is 73 degrees Celsius. 73 degrees Celsius is the answer. Now, the third one, calculate the decrease in temperature delta theta 2 between time equal to 90 seconds and time t equal to 180 seconds. So delta theta 2 is equal to 90 seconds, that is 72 degrees Celsius. Okay, that is 72 degrees. So this is 72 degrees Celsius minus 180 seconds, that is 65 degrees Celsius. So I'm going to put here 65. Right, so this is 65 degrees Celsius. That gives 7 degrees Celsius. So 7 degrees Celsius is the answer. And calculate the difference in temperature delta theta T between the temperature at time T equal to 90 seconds and room temperature theta R. So delta theta T time equal to 90 seconds. That is 72 minus room temperature, 72 degrees Celsius minus room temperature, 22 degrees Celsius, and I get 50 degrees Celsius. 50 degrees Celsius. Now, okay, let us look at the next one. D, a student suggests that the decrease in temperature of water in 90 seconds should be greater when the starting temperature is greater. The first part states whether the result agrees with this suggestion. Justify your statement by reference to the result. I would say yes, this is true. Why? Because the decrease in the temperature that starts from 95 degrees Celsius, right, which is at 0 degrees Celsius, right, it is 23. Right, within that 90 seconds, this is 23. But if I start from at 90 seconds, which is 72 degrees Celsius, right? Decreases to 72, okay? At 90 seconds, which is at 72 degrees Celsius, lower temperature, decreases to 65 at 180 seconds. The decrease in the temperature is 7 degrees Celsius. Right. So that is why the decrease in the temperature of water, right, in 90 seconds should be greater. Right. So I say that because justification, the decrease in temperature, okay, which starts from 95 degrees Celsius, yeah, within 90 seconds is 23 degrees Celsius, whereas the decrease in temperature, which starts from 72 degrees Celsius within 90 seconds is 7 degrees Celsius, which is true. Right, the second part suggests how you will continue the experiment using the same apparatus and method to investigate the suggestion. So I will say that I will just continue, yeah, with the experiment, okay, continue the experiment. Okay, for t equal to 180 second, t equal to 210 second, t equal to 240 second, t equal to 270 second, t equal to 300 second, t equal to 330 second. Okay, prolong the experiment, t equal to 360 second, right? To see the decrease in temperature. Yeah. So E, refer to table 3.1. Estimate the temperature of water in the beaker after cooling for a further 90 seconds. Okay, refer. This one we have to do some prediction. So I predicted, right? You see, they start from after cooling for a further 90 seconds, right? So 90 seconds. So I have to add, okay. I would see here, this is a decrease in temperature. This is 1 degree Celsius. Continue for another 90 seconds. So this is 180. So you take 180 plus 30 first. That will give you 210 seconds. This is at 30 seconds, yeah? I better put it here. Okay, when you add 30 seconds, you get 210 seconds. And then add another 30 seconds, right? You get 240 seconds. You add 30 seconds, right? 240 plus 30, you get 270 seconds. So this is 90 seconds. So it only decreased by 1 degree Celsius. So I say this one may be 64. This one may be 63. And this one may be 62. Right, so my prediction is that, okay, after another further 90 seconds, right, I said that maybe the temperature decreases to 61 or 62 degrees Celsius. I put 62 degrees Celsius. And the range given by the mark scheme is 59 degrees Celsius to 63 degrees Celsius. So I hope your value of the temperature is within the range, right? Now, my favorite parts, the last question here. Question number 4. A student investigates the effect of changing the color of light on the focal length of a lens. The focal length f of a lens is given by the equation f is equal to uv over u plus v. Distance u is the distance between an object and the lens. Distance v is the distance between the lens and the image that is formed on the screen. Plan an experiment to investigate with effect of changing the color of the light on the focal length of a lens. Now, the following apparatus is available to the student: illuminated object, a selection of color filters to change the color of the light, converging lens, screen, meter ruler. Other apparatus normally available in the school laboratory can also be used. In your plan, you should first part, draw a labeled diagram to show the arrangement of the apparatus. Let me show you. This is my labeled diagram. Here. Okay, now let me talk about my labeled diagram right here. I have a retort stand which I want to hold my lamp or filament lamp here, and this filament lamp needs a cell to operate. So I have a cell connected to the filament lamp plus a switch because I don't want my filament lamp to be overheated. Right, so this is my complete circuit for the filament lamp to work. And then I have a filter holder here because I need to fill in the colors, the color filter, right? So these are all the color filters. And then I have a lens here, but the lens, convex lens, cannot stand by itself. So I need a lens holder. You just insert the convex lens into the lens holder. That will do. And I have a screen here to move forward and backward to get the sharpest image here. And I have a meter rule to measure both U and V. Right? This is my diagram. Now, I am done with the diagram, so I'm going to put a tick here. And the second part, explain briefly how you would do the investigation, including the measurements you would take, right? So I am going to talk about that. That will be my method here. Methods, and I want to be polite. That is why I say set up the apparatus as shown in my diagram. Now, the second part, I would tell the examiner that I will measure my U using meter rule. Okay, I'll just put it here. U is measured by a meter rule. And first of all, I put in red filter. Okay, red filter is inserted in the filter holder. And then what did I say? Okay, this lamp. Okay, close the switch. Close the switch. And okay, move the screen. Close the switch so that the lamp will light up. Move the screen backwards and forward until the clearest image is seen on screen. Done. And then, okay, after that, measure your V. V is, okay, I am measuring my V. V is measured by using a meter rule as well. And after that, okay, don't just stop right there because the last point for the method is that you have to tell the examiner to repeat the experiment. Experiment is, oh, I forgot to calculate my F. Okay. Oh yeah, number 6. Before that, F can be calculated by equation F equal to UV, U plus V. Okay, UV, U plus V. And experiment, the last point is always this one. Experiment is repeated with maybe green filter, yellow. I would normally I would suggest the color yellow filter, brown filter, and maybe blue filter. And I'm done. And I have to put the tick here. Draw a suitable table with column headings to show how you would display your readings. You're not required to enter any readings in the table. Okay, I understand. Okay, I understand that. So this is my table. And I will put a color of a filter. And then I will put my U, which is in cm. And then I will put my V, which is in cm. And of course, F, right, is calculated. The unit of F is also in cm. How do I get that? You see, F is UV divided by U plus V. U is measured in cm, V is measured in cm, right? Cm times cm divided by cm. So you cancel one of the cm's, you left cm. So this is my table. So I try my best to draw a horizontal line for you here. Done. So if you want to fill in the color of the filter, you can fill in the color of the filter because I have already suggested it. But if you don't want, you just leave it like that. Doesn't matter. And the last part, state how you would use your results to reach a conclusion. Right, now I'm just going to put it here, conclusion. I would just say compare the color of a filter and F values to see the relationship. That is all about this paper, October, November 2023, paper 62. I hope you gain benefit from it. But if you have any doubts, any questions, any discussion that you want to make, please do comment below. I welcome your comment. Right. So thank you very much for watching. I'll see you in my next video. Bye.